All right, so last Thursday we finished up talking about reactions at the benzylic position, and we said that the benzylic position has really similar reactivity to allylic carbons. And then the first reaction we saw was this oxidation, where we can use chromic acid or potassium permanganate, and we can oxidize benzylic carbons into carboxylic acids. However, the most important feature is you have to have alpha protons coming off that benzylic position. If you don't, you're dead in the water there. The one problem with this technique is if you have other groups that can be oxidized, they will most definitely get oxidized as well. So in this example, we saw that alcohol get converted to a carboxylic acid. So if you do have an alcohol, what might be a good strategy if you don't want it to get over-oxidized? Protecting group, right? The protecting group we normally see used in the Klein textbook is what? TMS. The one problem with TMS, which is that trimethylsilyl, is it comes off under acidic conditions. This reaction is done under acidic conditions. However, there are a bunch of silyl-based protecting groups that you can use. One of the popular ones is called TIPS chloride. Does anybody know what TIPS might stand for? Triisopropyl silyl. So instead of having trimethyls or 3 methyl groups, you've got 3 isopropyl groups, and that won't come off under acidic conditions and can be used as a really rugged protecting group for alcohols.
I have a question about that one.
Yep.
So because that isopropyl group came off to become carboxylic acid, but why didn't that other substituent come off as well? Why did they both become carboxylic acids?
Oh, you're saying right here?
Yeah.
I guess to avoid confusion, just rule this out as an option. You're right. If you do have alpha protons, you run the risk of oxidizing right there. That's a fair point. Good catch. I was making up that problem on the fly. And then lastly, we said we can brominate the benzylic position by using MBS and heat. And if you don't remember this mechanism, please go back to chapter 11. The cool thing with this is that now we've got access to SN2 reactions, right? And we can do a bunch of SN2 chemistry using benzyl bromide. Alternatively, we can convert this into a Grignard. We can do a lot of really useful chemistry using this benzylic position, right? And so this is a really valuable intermediate for organic synthesis, and chances are, hint, hint, I might tell you you can use toluene as your starting material on either this next exam or the final exam. The other thing to note, too, is there's a bunch of reactions from last term that you can do. So, for example, let's say you want to convert benzyl bromide to benzyl alcohol. What conditions might we want to use? We have 2 options. SN2. If we do SN2, what reagent do we want? Yes, just sodium hydroxide, right? Strong nucleophile always favors SN2. But I'll tell you that this is somewhat unnecessary because you can do this with water. Why can you do this with water? What happens if that bromine pops off? Yeah, you've got a resonance stabilized carbocation. So you can actually do SN1 chemistry as well with these benzylic positions. They're incredibly stable when they form carbocations. All right, you can also do elimination chemistry from last term. All right, and with elimination chemistry, you can functionalize molecules pretty quickly. So let's say I've got this molecule, and I'm trying to convert this to a tertiary alcohol. And then I'm trying to make a styrene derivative that looks like this. What reagents would I need for each step here? Talk about it with your neighbor. You can have more than one step for every arrow. Yeah, you'll need multiple steps potentially. And let's see if we can even find a way where we avoid the alcohol too.
Because we can do E1. Yeah, you're
I guess you could do that. I mean,
yeah, we do acid count. Is that what you do?
Which step?
Or if you do E1, E2.
The first one on the bottom half? Well, then you do NBS and you to get a leaving group, but then that's not hard. You still need a leaving group.
NBS again, and we can do like
oh boy.
So we do NB8 once we get the chlorine first. And then we do
Oh, he did skip out the alpha. Yeah, you're right. We could do 2 steps.
All right, give me a thumbs up if you feel like you could fill out this reaction map.
I could bluff our way through it.
Let's do the first route on top. So can we convert that benzylic position directly to an alcohol in one step? No. But we just said we can first brominate it by using NBS and heat. And then in step 2, what can we do? Water, right? Okay, that would work. So we'll brominate it, do an SN1 substitution reaction. And then for step 2, what could we do to get to the alkene? Acid and heat, right? But I did hear Marcus say, what about tosyl chloride followed by a strong base? You could, however, you'd just be adding more work for yourself, right? So there's more than one way to go about this. For the second one, we can also get there a lot quicker. And we could say, you know, we could use NBS and heat followed by what? Yeah, something like a strong base, terp-butoxide. Really, any strong base would work. But let's do terp-butoxide just to avoid the potential of any sort of substitution occurring. So a good non-nucleophilic base. And then now that we have this alkene, we could do all of the reactions from chapter, what was that, 9 or 10? I think it was chapter 9. And then with alcohols, we can do a bunch of variations on alcohols. We could do Regio Chemistry. There's a whole bunch of reactivity we can do here. So if you still have that reaction map that you were building on earlier this term, you could start adding in more and more arrows to this. There's a little summary of reactions in your book, too, that kind of shows the potential uses of this. So, for example, in that top left-hand corner, we just talked about brominating it or oxidizing the benzylic position. And then we can make it into a benzyl alcohol, a tertiary alcohol, or we can make it into an alkene. And we've got a whole heck of a lot of reactions we can do branching off of there. So if you can, try to work and finish up your reaction map before the final and try to make your complete Chem 262 reaction map by the weekend. All right, one last reaction. And this is the reduction of aromatic compounds. And there's a kind of odd reaction, but let's do a little bit of review. What's this parent called? Styrene, right? So it's a monomer used for making plastics. And if we do hydrogen gas and something like palladium on carbon at low pressure, what will get reduced? The alkene, but will the aromatic ring?
No.
No, because we said the aromatic ring has this stabilization. And so what would this molecule be called? ethylbenzene, right? So in this case, we can't say it's a toluene derivative. Toluene has to have that CH3 only, but this would be ethylbenzene. And then if we want to reduce ethylbenzene, we really got to push on it. And typically, in order to do this, you actually have to even go to a special lab. Most labs don't have the equipment to do this. And you use a special nickel catalyst, and you crank this up to 100 ATM, which is a lot of pressure. So this isn't something you'd do in your sophomore organic class. But you can convert this to ethyl cyclohexane, right? There is another reduction that's a lot more common, and this is called the Birch Reduction. And the Birch Reduction is a partial reduction. We're not going to reduce the entire aromatic ring. That takes a lot of energy. But instead of doing that, we're going to convert it to a diene. So I'll show you guys the overall reaction, and then we'll go through and do the mechanism. This is another reaction where you use elemental sodium, so you'll see it written as Na dot. And then some sort of alcohol, oftentimes methanol, but you might see tert-butanol or ethanol. It doesn't really matter as long as it's an alcohol. And then ammonia. And when you do this, you make a diene that's non-conjugated. And then you can do all sorts of alkene chemistry off of this.
Is that liquid ammonia?
Yeah, so ammonia is normally a gas, so this is typically done in a pressurized vessel or with some sort of dissolved ammonia in your alcohol.
Can you further reduce that like you would the other ones?
Yeah, so at this point, each of those alkenes is much easier to reduce. So you could catalytically reduce each of the alkenes in here. But let's take a look at the mechanism. And if you remember the dissolving metal reduction with the alkenes, the sodium was acting as an electron donor. Because it's got an electron, it's very reactive. It wants to form a sodium cation. And so in this case, it's also going to be a reduction where that sodium gives its electron to one of the carbons. So let's take a look at our benzene ring, and I'm going to draw in all of our hydrogens. This feels like fall term again. I know, I feel like I'm going so slow when I have to draw out all my hydrogens. Okay, so in this reaction, sodium is going to give an electron to one of these carbons. And when it does that, another electron is going to hop over too, because electrons want to be paired. And then the remaining electron from this pi bond is going to hop over here, and then it's going to get paired up with an electron from that pi bond. And then last but not least, this remaining electron will get shuttled down to the bottom. This looks complicated. It's kind of like a carousel of moving electrons. However, there's a really interesting intermediate that's been experimentally proven. Where now this top carbon has 2 electrons and this bottom carbon only has 1. So just like with our dissolving metal reduction with alkynes, we have this radical anion intermediate. This radical anion is incredibly unstable, right? It doesn't look very happy to me. And so what it wants to do is it wants to steal a proton from your solvent. So our solvent in this case is methanol. However, like I said, it could be any alcohol solvent. And this lone pair is going to just grab one of these protons and pluck it off. And now that we've got our anion, it wants to steal one more electron from sodium. So another equivalent of sodium can give up its electron. And remember, anytime you're moving single electrons, to have those fishhook arrows, not the double-headed arrows. And we'll go ahead and we'll just make an anion. Okay, and then last but not least, what do you think is going to happen?
Alcohol.
Yeah, it's just going to steal another proton from your alcohol. Oh, let me clean this up. And after this step, you've got your 1,4-diene. Does that make sense?
What's the point of the ammonia then?
That's a good question. In this case, I think it's just what's been experimentally useful. It's not the proton donor because it's not nearly as acidic as the alcohol, but I think it's just used anytime you're doing a dissolving metal reduction.
So it just stabilizes it.
Yeah, that's a good question. I should look that up. All right, so this is our overall mechanism. However, we do have to pay attention to our Regio Chemistry. So let's take a look at the Regio Chemistry.
I have a question on that.
Yeah.
Where do you initially get, so why do we have a sodium radical out of nowhere, and then we have a sodium ion on the other end?
So that's a good question. So the sodium radical that we're looking at is just elemental sodium. That's metallic sodium that you've thrown into this
But that is a
solution.
radical later on, right?
So elemental sodium, by its very nature, is a radical. It has an unpaired electron. So sodium, like we said, is really, really soft. It's a malleable metal you can cut with a butter knife and then huck into your reaction mixture. After it gives up that electron, it becomes a sodium cation that will dissolve in your reaction medium.
Okay.
So let's take a look at the Regio Selectivity. And I'll take two examples. Oh, let's do this example here. And we've got two potential options, and we have to figure out which one's more likely than the other. So one option is that our dienes are formed in this orientation, or our second option, is that our dienes are formed in this orientation. So we have to rationalize which one's more likely to occur. And what I like to do is I like to look at the group coming off of the benzene. So in this case, we've got a ketone. And then identify whether or not this group is electron donating or electron withdrawing. So what I mean by that is the substituent capable of pushing electron density into the ring via resonance, or can it pull electron density out of the ring via resonance? What do you guys think? Is it going to push electrons in or pull electrons out? So can I take one of these lone pairs and kick it down? No, that would violate the octet rule. Can I take this pi bond and kick it down? No, again, that would violate the octet rule. We'd have Texas carbons. I'd be very sad. However, what this can do is it can pull electron density up to that oxygen, right? So in this case, this group is considered electron withdrawing. Whoop. Okay, I'm going to just erase these arrows for right now. Whoop. Okay, so we've identified our substituent as electron withdrawing. Next thing I do after that is I look at the carbon coming, or the carbon where that group is attached. And in this case, do you think it wants electrons? Or do you think it doesn't want electrons? Wants them, right? It's getting electrons pulling away from that carbon, so it wants electrons. So let's make a note. This wants electrons, which means it is likely to be reduced. Yep. Okay, so which one of the products has a carbon that's been reduced? The left one or the right one?
You mean the one in that position?
Yeah, so is this the one where this carbon's been reduced, or is this one have the carbon that's been reduced?
The one on the right.
The left, right?
Ooh.
Reductions gain of electron. There's a hydrogen over a carbon. Carbons tie, hydrogens gain.
Yeah, reductions gain, right? So if we went through and we did the oxidation number for these, going from here to here, there'd be no net change for that carbon, right? However, going from here to here, we would have a reduction at that position, right? So in this case, we can predict that this would be our product, which is correct, and this one is not observed. All right, let's do another one. So with this one, again, we're running into the same sort of situation where we have to ask ourselves, all right, are the double bonds going to be in this orientation or in that other orientation? So we've got what parent molecule here? Anisole, right? Or methoxybenzene if you want to use the more traditional name. Is this going to be electron donating or electron withdrawing? Donating. We can most definitely push these electrons in. So this entire group is going to be electron donating. There's no way to pull electrons out of the ring without violating one of the octet rules. Okay. So if that's electron donating, again, I look at this carbon where it's attached. And in this case, it does not want electrons. Right? So if it doesn't want electrons, which of these two products is more likely, the left one or the right one? Right one. This one is not observed. Does that make sense? All right. Yep.
So I know oxidation's backwards because that's just the way the history has been. But so for the first one, it lost a pi bond. It's not losing electrons. So why is that one? It seems really backwards.
No, that's a good question. So let's just, for the sake of argument, go through and look at this carbon right here, right? For this first one, what's the oxidation number for that carbon? Yeah, it's 0, right? So this one has an oxidation number of 0. If we look over here, what's the oxidation number now? -1, right? It gained a hydrogen. Carbon's more electron withdrawing than hydrogen, so it gets both of those electrons. So oxidation of -1. That means that this was a 1 electron reduction. And we know that that's most likely to occur at that position because that's the position where the electron withdrawing group is attached. Does that make sense?
Even though there's a pi bond on the right figure, which means that they have more electrons there. Okay.
Yeah, another way of thinking of a reduction, right, is reduction's often accompanied by a gain of a hydrogen, right? So if we look at that top carbon, it gained a hydrogen, therefore it was reduced. It's the same concept with reducing an alkene, right? When we reduce an alkene, we're essentially putting 2 hydrogens onto the alkene. That's another way of thinking about it. Let's try another more challenging problem, and I'll give you guys a minute to work on this. But what I want you guys to do is to provide the mechanism for this. Okay, so let's do... Actually, let's do it this way. And let's do a Birch reduction. And then once we determine what the product would be, let's try to fill out the full mechanism. So I'll give you guys a minute to work on this, but try to check with your neighbor and see if you agree. And I'm just going to circle our substituents, and then we can go through and label them as electron donating or withdrawing, kind of like we did previously. Just so we're all on the same page, this methyl ester up here, is that electron donating or withdrawing? Withdrawing, right? So in this case, I'm just going to label this EWG. What about this dimethylamino group down here? Is that donating or withdrawing? Donating. That lone pair can be pushed in. So I'll label this as electron donating group, EDG. All right, and then what about a methyl group? It's not very electron withdrawing or donating, right? Because you can't push electrons in any way, shape, or form, which means it's not going to have a huge effect. However, one thing I will tell you guys is typically alkyl groups are thought of as weakly electron donating due to hyperconjugation. So do you guys remember talking about hyperconjugation? The sp3 lobe can stabilize the adjacent p orbital. Therefore, it's acting as a weak electron donor. So this is weakly electron donating.
When you say that double those lone pairs can be pushed down, you don't mean push down the sense of a bond there, right?
So if we try to draw resonance structures, right, we could push electrons into the ring from that lone pair, which makes it electron donating. With that top one, there's no way of pushing electrons into the ring without violating rules.
But wouldn't that be breaking aromaticity?
It would be, but it's still a valid resonance structure, right? With resonance, it's not that we're making or breaking bonds. It's just that certain carbons have higher electron density than others. Okay, so now that we've identified our electron donating and electron withdrawing groups, which carbon is most likely to be reduced? The top carbon, the bottom carbon? Which carbon do you guys think? The top one, right? So we could go through and we could say we know that the carbon that's attached to our electron withdrawing group is most likely to be reduced. Okay, so I think we've got all the information we need, right? So if we go through and we draw our product, we know this top carbon is likely to be reduced, which means it's going to have an additional hydrogen coming off of it. That means our dienes must be on opposite sides. This dimethylamino group must be coming off of this position, and this methyl group must be coming off of that position, right? Does that make sense? And if you notice, these carbons right here and right here haven't been reduced, which fits that electron donating scheme. We don't ideally want those carbons to be reduced. What we'll talk about next term is not all electron donating groups are created equal, and not all electron withdrawing groups are created equal. Sometimes there's a tug of war, and one will win out. However, we haven't even gotten there yet, and I'm not going to throw some curveball like that at you on the exam. All right, do you guys want to do the mechanism for this one?
Yeah.
Have you guys done it on your own yet? I'll give you guys another couple minutes, but try to work through the mechanism and then check with your neighbor to make sure that all of your arrows are correct. And I'm just going to go through and draw my skeleton structure real quick.
What's the abbreviation for ester? So like EST?
I would just draw it out. Yeah. And then once you think you got the mechanism, give me a thumbs up so I can see a few people. I'm going to draw in my starting material, and then we'll add electrons and double bonds as needed. The Birch Reduction is actually still used in a fair amount of natural product synthesis. In fact, if you go through the practice exam, one of the practice problems I put on there is from a total synthesis paper.
Who uses the most organic chemistry? Lab techs?
Who what?
Lab techs? Do lab techs actually use synthesis the most?
Usually it would be a research scientist or a graduate student or a postdoc, somebody like that. You typically don't just hand out sodium to people willy-nilly because it's a fire hazard.
Can it melt, or can it like catch fire from the air?
Yeah, if you live in a moist environment, there is a risk of it catching on fire. However, sodium is relatively unreactive. The biggest problem is when you go down to potassium. Potassium's a lot more reactive. All right, so let's go ahead. We know this top carbon wants this electron. So we have to be careful to use our fishhook arrow. This electron's going to hop over from that pi bond. This electron's going to hop down. This electron's going to hop over. And then last but not least, our electron's going to end up on that bottom carbon. So we've already formed our diene. We've got this anion down here, and we've got this radical on the bottom carbon, right? In the next step, we know the anion wants to steal a proton from the solvent, which will make it neutral. And then we have this radical that's left over, and it wants an electron from our second equivalent of sodium. After that step, we've got this anion down on the bottom. This anion can grab this proton, dump electron density over to that oxygen, and give us our final product. Make sense? So oftentimes with the Birch reduction, I try to predict what my product would be before I do the mechanism. That way I know where to deliver that first electron to. In that first step, we need to know where that sodium is giving up its electron. All right, we only have 5 more minutes. But what I have for you guys is synthesis practice problems. So if you don't have a chance to get through all of these right now, I'll leave them in the course notebook, and then a little later I'll put up the key for this. However, if you have the study guide, you can pull up the answers in there too if you're impatient. So I'll give you guys a minute to work on this, and you guys can check with your neighbors, and then we'll probably have to leave